Welcome back, sports fans. It's a cold Monday here in Bethel, and we're going to do some trigonometry. Remember, what is the area of a triangle? Now let's think about it. So here is a right triangle, as right as I can draw it. And back in the day, so here's the base, here's the height. And they told you that the area of a triangle is 1/2 the height times the base. Or the base times the height, either way, it doesn't matter. How did they figure that out? Well, before you knew trigonometry, what they would do is they would go, hey, look at what this really is. This is this rectangle. The area of a rectangle is the height times base. Clearly, the triangle only takes up half of it. So there's that. Okay, so now, let me try and get another drawing up here. How would you find the area of a triangle that doesn't, if it's not a right triangle, it may not have a well-defined height. That's easy to figure out, right? Just by the picture anyway. We'll take a look at this. Give me a sec to draw her up here. So triangle, we'll put B up here. And so this is here. Remember from our laws of sines. So now, what do we need to figure out? Well, it is, the area of a triangle is 1/2 the height times the base. What's the height? Well, the height is here. All right, so here's the height. Here's the base. This is still the base. Oops, that's terrible. So what is this? How do I find this? Well, let's think about it here. This is, so for this angle right here, let's let this be angle C, right, as this is coming along. And now, make another drawing and remind you of some things. So here we are on the unit circle, or actually we're just, well, I'll make it the unit circle. And here's this. This is what this is supposed to look like. This is the angle C from this picture right here, right? However, the picture that we use to figure out the sines and the cosines is this picture right here. Right? Okay, so sine of C, here's the hypotenuse of the particular triangle we're working on. That's little a. So this is going to equal h over a. So that means that the height is going to be a times sine of C. And now we have h, so we know that the area is going to be 1/2 h, which is a sine C, times b, and usually, which is the base, and usually you write it like this, 1/2 ab sine C. So that's all there really is to it. There's one more formula that I'll put up here, and the book didn't even give the general name of it. The area of the triangle is also given by this. You're going to love this. S times S minus A times S minus B times S minus C, where S is equal to 1/2 A plus B plus C. This is called Heron's formula. And at some point before computers, before something, this must have been very famous and useful because it shows up in every textbook. I have never once seen a useful use of it. It's just it's a somewhat obscure relic at this time. I don't know, I've never bothered to memorize it, I'm just aware of it. I think that what you probably don't know is that before calculators, where did they figure out the sine? Suppose C is 43.21 degrees. How do you figure out sine of C then? Well, what they did back in the day was they made tables. They employed mathematicians to sit and toil endlessly and figure out approximations for these by using their trigonometric expansions. by using polynomial expansions. One of the things you'll learn in Cal 2, hopefully you'll go that far, is Taylor's theorems. And what you can find out using Taylor's theorems are these, which I'll write up for a second, because we're going to go into complex analysis pretty much the next lecture, and I'm going to show you some really, really cool stuff. But you can prove, and I usually make my students prove in the Calculus 2 class, that it is a remarkable fact that you can write cosine x as this infinite polynomial, which is 1 minus x squared divided by 2 factorial plus x to the 4th divided by 4 factorial minus x to the 6th divided by 6 factorial. I'll do a couple more, plus x to the 8th divided by 8 factorial minus x to the 10 divided by 10 factorial. Boing, 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 boing. It keeps going on. And similarly, sine of x can be written as x minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial minus x to the 7th divided by 7 factorial, and it goes on and on. As I said, in Cal 2, you will derive this. Incidentally, if you haven't seen this factorial, 5 factorial is just 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. In general, n factorial is just n times n minus 1 times n minus 2 times 1. Right? That's just what this notation means. So basically what you had was a bunch of guys sitting in a room, probably lit by candles, or sun if they were lucky, and they probably approximated the sines and cosines for any number that you might between, probably actually mostly in the first quadrant, I would guess. I don't know, I should research this. There used to be, when I was a kid, there were books that were just tables of trigonometric values. That's it. That's how you used to have to figure out what the sine of 43 point whatever was. More recently, before calculators, there were slide rules and things, but basically there were a bunch of folks that just made their living doing these rather long and tedious calculations. So now you get to do long and tedious calculations. I'm not even going to do a problem for the area of a triangle. What I put down there, 1/2 AB sine C. I mean, once you look at the picture, this is a plug and chugger. Make sure that you do a couple problems with it. In the meantime, I'll see if I can find some actual use or some historical knowledge about Hennon's formula, and just to see why this is always included in textbooks. I'm sure it's rather clever how it was derived. And I think now we're going to start complex analysis.